When a vehicle travels at highway speeds, it is constantly bombarded by cosmic radiation. If a high-energy neutron from the upper atmosphere slams into the silicon lattice of a processor, the impact temporarily alters a memory cell's electrical charge. Modern autonomous driving systems are entirely dependent on neural processing units, or NPUs. These AI accelerators execute trillions of complex matrix operations per second to interpret sensor data, and they are forced to do so while exposed to this harsh, radiation-heavy physical environment. If an electrical disruption hits a traditional electronic control unit, the system has standard defenses. Hardware exceptions, operating system panics, or watchdog timers detect the lockup and instantly trigger a fail-safe mode, safely pulling the vehicle over. NPUs behave differently. When a physical fault strikes the deeply embedded mathematical data path of an NPU, the operating system registers absolutely no exception. The hardware continues executing instructions perfectly, but with corrupted numbers. The neural network processes this flawed data and outputs a confident but entirely incorrect classification, like identifying a pedestrian as an empty stretch of road. Because the system's standard monitoring tools remain completely unaware of the error, the failsafe mechanism is never activated. This phenomenon is known as silent data corruption, or SDC. It creates a silent failure that bypasses every traditional safety measure in autonomous engineering. To catch an SDC, we have to isolate exactly where the fault occurs. The targets are the microscopic processing elements, and specifically the multiply accumulate, or MAC units, densely packed inside the NPU. When a cosmic particle or a sudden voltage drop strikes a MAC unit, it causes a soft error, known as a single event upset. This transient interference contains just enough energy to flip a single bit of active data from a 0 to a 1, or vice versa. A bit flip of this nature evades standard parity checks because it skips the processor's control logic entirely. The error originates purely within the mathematical payload flowing through the arithmetic logic unit. The operating system manages software logic, not the intermediate math inside a hardware accelerator. To understand how a single flipped bit scales into a fatal vehicular miscalculation, we must look closely at the NPU's architectural design. The defining engine of a modern AI accelerator is the weight-stationary systolic array. Instead of constantly pulling information from main memory, this grid is designed to pass data sequentially from one processing element directly to the next, maximizing computational efficiency. Traditional GPUs rely on independent threads processing separate data paths. If an error occurs, it remains localized and is often masked by surrounding threads. The systolic array, however, is a deeply interconnected pipeline. If a single MAC unit inside this grid suffers a bit flip, the resulting error does not stay contained. Because the array passes data forward, that one corrupted processing element systematically infects every piece of activation data that passes through its column. By the time the calculation exits the hardware grid, that single microscopic failure has compounded, polluting an entire column of the output feature map. This tightly coupled pipeline provides the raw speed required for autonomous driving, but guarantees that a single hardware flaw will cascade, destroying the network's accuracy. Once the corrupted feature map exits the systolic array, it moves into the neural network's nonlinear activation layer, where the error undergoes a dangerous transformation. Neural networks rely on the ReLU activation function to parse complex patterns by keeping positive values as they are and converting all negative values to 0. If a bit flip forces a normal number into a massive, corrupted negative value, the ReLU function instantly truncates it to a harmless-looking 0. By forcing the broken value to 0, the algorithm unintentionally scrubs the mathematical trace of the hardware error entirely out of the data path. When the hardware watchdog scans the output, it sees only valid 0 data and raises no flags, silently inverting the downstream probability distribution. The AI processes the missing data and outputs a clear path forward, accelerating the vehicle directly into an obstacle. Aerospace engineering handles radiation by using triple modular redundancy, running 3 identical processors and voting on the outcome. Applying that level of physical redundancy to a dense AI chip requires too much silicon area and exceeds the vehicle's power budget. To protect the vehicle without tripling the hardware, engineers implement algorithm-based fault tolerance, or ABFT. Look at these two matrices multiplying. ABFT defends the calculation by appending dedicated checksum rows and columns to the edges of the input matrices before the math begins. The hardware calculates the checksum alongside the main data payload. For this to work, the final comparison must be processed by a completely isolated, dedicated extra MAC unit on the silicon. If the primary processing element calculated its own checksum, a single bit flip would corrupt both the data and the answer key simultaneously. Isolating compute logic from verification logic ensures the hardware catches faults internally, maintaining the real-time inference speed necessary for highway driving. Strict ABFT catches single bit flips, but it also triggers false alarms. Deep learning models use quantization to compress data, and fixed-point math generates minor rounding errors. A strict verification system interprets these tiny discrepancies as hardware faults, wasting vital compute cycles on unnecessary recovery routines. This table displays an NPU memory register map. To handle rounding errors, the software driver interacts with the ABFT thresh hardware register. This interface sets a dynamic error threshold, instructing hardware to ignore acceptable quantization noise while still trapping massive data spikes. Yet, quantization introduces a separate threat at the memory level. The NPU fetches data from the global memory over an AXI system bus, grabbing information in rigid 64-byte chunks. To process a highly compressed 8-bit integer model, known as INT8, the hardware requires the incoming data to align perfectly to a strict 16-byte boundary. If the AI compiler makes a stride error and the data is misaligned, the hardware cannot read it cleanly. It is forced to pull overlapping cache lines and perform dynamic bit shifting. If mixed precision operations are running, the hardware will misinterpret a single 16-bit floating point payload as two separate INT8 integers, filling the pipeline with garbage data. The NPU processes this meaningless data without generating a single system trap or error message, leading to a total output collapse of the neural network. A perfect hardware safety net becomes useless if the software compiler organizes memory incorrectly. The vulnerability embeds itself into the AI toolchain. While cosmic radiation causes random, localized hardware faults, software faults generated by the AI compiler act differently. They are systematic. The recently established ISO-PAS 8800 standard addresses this directly. It mandates that the AI toolchain, from the data labeling framework down to the model compiler, must be validated as a critical safety component rather than treated as an offline utility. A single compiler bug, like fusing an activation layer and a normalization layer in the wrong sequence, creates a deterministic error. It silently deploys the exact same mathematical failure to millions of vehicles simultaneously via a firmware update. To block corrupted compiler logic from reaching the NPU, engineers deploy a defense at the interface level known as command stream CRC validation. In this diagram, a stream of hexadecimal command blocks flows directly into the hardware parser. As the NPU fetches these instructions, a scanner calculates a cryptographic checksum in real time, verifying it against the original signature generated by the compiler. If even a single bit mismatches or an uninitialized memory address is detected, the NPU hardware instantly halts the execution pipeline. Safe hardware is designed to actively distrust the instructions provided by its own software. Even with an uncorrupted toolchain, autonomous vehicles eventually face out-of-distribution data. The AI encounters chaotic physical conditions, sensor noise, or environmental elements it was never trained to understand, leading to highly unpredictable mathematical outputs. The final safeguard against this unpredictability is the deployment of formal runtime monitors. These monitors are automatically synthesized from a rigid mathematical language known as signal temporal logic. Running in C++, these monitors evaluate the NPU's output using fixed ring buffers. Because they operate in constant O1 time, they process the safety checks instantly, adding virtually zero latency to the vehicle's reaction time. Watch how this expanding geometric swarm, representing chaotic AI predictions, strikes and bounces off a rigid perimeter shield. The runtime monitors enforce a strict mathematical boundary. They deterministically trap erratic object trajectories and impossible steering commands before those signals can ever reach the vehicle's braking or steering actuators. The integrity of the autonomous system relies on a vertically integrated architecture, a sequence of mathematical proofs spanning from the cryptographic signatures of the toolchain down to the real-time status of the silicon registers.